Okay. Okay, so if we're all here, I'd like to begin the dances. For those of you who are following us live and who may be tuning in just now, welcome to, as part of the CIMEC Open Day, this is the Doctoral Student Day 2020. This morning we introduced the educational offerings to prospective students, both in the master's and the PhD program. And now we will begin with the DS Day, Doctoral Student Day 2020. I'll introduce myself. I'm Leah Mercanti. I am the administrator of the PhD program. I'm filling in actually for Professor Zampini, who couldn't make it today. So before I begin, I'd actually like to thank, first and foremost, the PhD students who organize every year this event. It's now in its 10th edition. So I'd like to invite everyone for an applause to the organizing committee, and I'm not sure I remember who everyone is, but please stand up if you're here, and thank you for organizing today. And also for all the time you put into reading the abstracts, of course. DS Day is, as you can see here behind me, it's a moment for the PhD students to show what they're working on and to allow interactions and reinforce interactions between all levels of researchers here at the CIMEC. That will happen both through the 3 talks that we're going to have now and by the poster presentations happening later on this afternoon. There's a coffee break also later on. There will also, there's a committee apparently evaluating all of the posters who are anonymous. And at the end of today, we will be here again at 4:30 to give the awards to the best talk and the posters. So the speakers we have this afternoon are starting with Francesca Saviola, who's a second-year PhD student, followed by Ludovico Coletta, third-year PhD student, and Shahriar Noé, who's a second-year PhD student. So let the games begin.
Can you hear me? Okay, perfect. Good afternoon to everyone. Today I'm gonna talk about our ongoing project in collaboration with the neurosurgical unit of Santa Chiara Hospital in Trento. And this project title is Post-Surgical Human Brain Functional Reorganization in Gliomas, a longitudinal study. So this is just a brief outline of what I'm going to talk to you about. We will just start with a little bit of background and the study rationale. Then we will switch to study aims. I will talk to you more deeply about which is the sample of our patient. And then we will go more deeply in materials and methods, talking about functional connectivity analysis, and then try to put all things together in our results section and trying to draw a major conclusion and the further direction for this project. So the main idea behind this study is that gliomas was previously known as a focal disease, but still we know that the presence of a tumor can cause changes in brain connectivity. So the idea was to better understand how large-scale functional brain networks, such as the default mode network and the frontoparietal network, can be changed due to the presence of a tumor. And we know these two networks in particular can be considered as hubs network in the sense that they represent the most wired area connected of the brain. So we end up investigating functional connectomics of brain tumors, and in particular, we want to know what happened to these hubs functional connection. Will they be impaired? So we know from literature that brain gliomas are characterized by alter network properties, and in particular, there are segregation properties and integration properties which are different compared to healthy controls. And moreover, as I was saying before, these hubs connection change both structurally and functionally as a result in a general decrease in efficiency of the network. We also know that cognition can be associated to functional brain network, and particularly in gliomas at baseline, the cognitive domain can be characterized by network connectivity. So with our study, we ask ourselves, okay, can we put into this framework a longitudinal aspect? And we start trying to think how to predict, by means of cognitive, functional connectivity, changes in longitudinal brain tumor. So the first point of this project, we'll talk about neuropathology, so how the brain changes due to the tumor present longitudinally, but also which is the response to the treatment in the patient, and which will be its cognitive profile longitudinally, so by adding the temporal trend. And going more specific, we will start talking about the neuroplasticity, so the functional connectome of our brain tumor patient. And we all know that brain connectivity subserves, in some sense, cognition, but we don't really know what happens if the system is perturbed. So in our case, we will have a tumor, then the neuroplasticity will be affected by the spread of the disease, and then this will some way impacted by the fact that we'll have a treatment. So in first place, we will have a treatment which can be brain surgery, but also can be an oncological treatment, so radiotherapy, for example. But we also want to know which is the outcome of this patient. So what will happen when we will ask to do a task to the patient, and he will have some cognitive load, and he will have a behavioral performance which in some sense can be different to the one he did have at baseline. So this is our sample. As you may see, we did have two main types of tumor, low-grade gliomas and high-grade gliomas. And then we did collect also some tumor characteristics. So for example, tumor hemisphere, so lateralization, then tumor volume, tumor mutation, which is an index, a negative index of outcome, and tumor methylation, which is a positive index of treatment response. And this is just a tentative flow chart of this study. So at baseline, we did collect pre-surgical MRI and baseline neuropsychological assessment. Then our patient underwent surgery, and then you can see there are two main paths. The first one is just for low-grade gliomas, for which we have collected our first follow-up with both MRI and neuropsychological assessment 3 months after the surgery, and then 6 months after that we repeated the test. For what concern high-grade gliomas, we did have a change. So we did have also a treatment, in this case, a radiotherapy treatment. And so we did our first follow-up after the end of the radiation treatment. And then we repeat the test 6 months approximately after that. So for what concerns the functional connectivity analysis, we have started from the resting state of MRI bold API. We have preprocessed our image with our time course, and then we have parcellated the brain. We have used a functional brain parcellation since we know that we will use API bold fMRI to construct our connectome, and in this case it was better to have a parcellation who reflect directly the resting state ICA-derived networks. So we end up with our functional connectome, and then we construct our matrices. But we also construct specific matrices for the hubs property of this network. How did we do that? So we started from the general functional connectivity matrices, and we start from the definition of hub region. We have decided to define anatomically, in some sense, the hubs region, since we know that functional connectivity is globally altered in brain tumors. And in this sense, we will not be able to predict reproducibly in all our data set the hub's properties. So it wasn't difficult to extract this metric, let's say, by using, for example, graph theoretical analysis. That's why we choose hubs region to be a priori defined. Then we construct 5 different matrices for each subject. The first one is a functional connectivity matrix within hub. What I mean that the hubs region we were previously selected, so the frontoparietal network and the default mode network together was constructed to be in the same matrix, and we then construct the functional connectivity between this region. Then we have 2 subsets of different hub properties, specifically for each network, and then we will have another matrix who talks about the connectivity between hubs region and non-hub regions. So all of the other regions that do not belong to default mode or frontoparietal network. So for example, motor cortex. And then as a last matrix, we did test also connectivity within non-hubs regions. So again, all regions that do not belong to frontoparietal and default mode. And then we just put all of these metrics in our statistical analysis with linear mixed model. We did use 2 different models. The first one was for testing the behavioral scores, so just using the neuropsychological variables we had. And we did include, as a predictor, tumor characteristics, for example, such as lateralization and tumor grade. Then, by using the same model, we want to test also functional connectivity difference. So we want to see how functional connectivity can be predicted by all of these predictors. And we add also the neuropsychological measure here that were previously resulted statistically significant in the other model. So for what concerns the neuropsychological changes longitudinally, we have seen that for the memory domain, we have a dissociation pattern. So post-surgery, there is a decrease in short-term memory score in our sample, whereas there is an increase in long-term memory score. Also, we did detect a change in a language domain, and there is an improvement in naming. The really interesting thing is that these changes are irrespective of tumor stage. So, for example, there were no differences between high-grade gliomas and low-grade gliomas. So, for what concerns instead functional connectivity, talking about hubs connection, particularly we detect a change in a subset of the DMN, and we detect a positive, significant longitudinal effect in functional connectivity within the DMN. Another positive effect was found for connection of hub, non-hub. So if you remember, we were saying that hub are default mode and frontoparietal, and all of these connections are in relationship with all the non-hubs region. And in this case, again, we have detected a positive longitudinal increase in this connectivity. On the contrary, for what concerns non-hub regions, so the one in green, we have detected a negative effect on functional connectivity on time, so longitudinally. So how can we bring together all of these results? We know that long-term memory improves with time in our sample, and we also know from literature and from our analysis also that long-term memory can be associated with functional connectivity within DMN. On the other hand, short-term memory worsens in our sample. And this is also associated with the other hubs network of the frontoparietal network, which is more relative to executive function of memory. But longitudinally, we did just detect an increase in functional connectivity in the DMN, whereas for the frontoparietal, we didn't detect anything. So this may allow us to say that there is a potential functional compensation mechanism going on, which allows the patient to maintain the behavioral performance in the case of the functional connectivity increase in the DMN, and which doesn't allow instead the patient to maintain the same performance for short-term memory because the frontoparietal network is not showing any change. And this is, again, irrespective of tumor stage and grade. So what happened more at a macro scale? As we were saying before, there is this positive trend of hub and non-hub connection, which is trying to re-establish longitudinally in the brain tumor patient brain efficient connection, because you may imagine that a connection that brings an hub out to a non-hub region has an integrative function, whereas connection within a non-hub region can be considered as a higher way of segregate. But we know that in the normal brain, non-hub regions are not that modular. So this can be seen as a way of the tumor brain to reestablish the connection present once. And this again is irrespective of the tumor stage. Finally, to sum up, I would like to add some further direction. We are trying to understand how to better take into account the tumor effect in our analysis, because we know from literature that the tumor affects the bold signal. However, in our case, we cannot just simply masking the tumor, because this will affect our parcellation. And there is a high heterogeneity in our group that would not allow just to remove the tumor parcel, because they are all spread all over lobes, for example. So we are still working on it. And moreover, we want also to add some interaction model to better understand if the staging and the treatment effect that we are not catching in our analysis can be catched by means of interaction model. So just to try to sum up all of these results, this is the first longitudinal study which tried to investigate functional brain reorganization and cognitive profile of patients longitudinally. And for sure, this highlights the role of network hubs in the patient recovery, with particular attention on the cognitive profile of the patient. And this may allow us to say that considering this functional network to be relevant to minimize the damage needs to be done in pre-surgical planning. I would like just to thank the funding for this project, and of course the neurosurgical team led by Silvio Sarubbo, and the neuropsychology Luca, who did collect all the data, and all the MR methods group, and particularly Domenico, who did the data validation of the pipeline and the acquisition protocol. Thank you.
Okay, I think you know me. I'm Costanza Papagno. I really enjoy your talk. It was a very nice work, but I would like to point your attention to a couple of things. One was the short-term memory part. These tests that you put there were not short-term memory tests, so you cannot say that there was a decrease in short-term memory, because one is a copy test, the copy of the ray figure. You have your figure in front of you, and this remains until you end with the copy, so there's nothing on memory. And the immediate ray words, this is a learning test. Shorter memory tasks, by definition, are span tasks, so digit span, course span, etc. So you have not a deterioration of shorter memory. You have just a deterioration of copy and of learning, okay? The other point is, this is a question. Did they use, for the neuropsychological assessment, different forms of ray figures and ray words? Because if you use the same, there could be a learning, because they repeat the same task. So this is the reason why what we do, I work with tumor patients, is to use parallel forms of ray figure or ray words of words, so that you can avoid improvement. Because indeed, since these patients are not really amnesic or very deteriorated, they can just learn the fact that they are reproducing the same figure. And also because the ray figure is in incidental learning, so the first time you present the figure and you don't say that they will have to copy the figure. While when you do this once, the next time you know that they will ask you again to reproduce the figure. Okay.
These are good points. I was wondering if, since I didn't have in charge in neuropsychological part, I see your point about short-term memory. I was wondering if in investigating copy of ray figure or ray immediate ray words, there were like a visual part of short-term memory, if we can say, or not. Okay. Okay, I see. Okay. I do not have the answer about the learning part. I was worried about that too, and we for sure need to better investigate the trend and to ask Luca, who did collect the data about this. Yeah, for sure. Thank you.
Did you consider in your data processing to normalize or to take into consideration for the location of the tumor? And if not, how can you consider these? You just told us that, as expected, tumor location is extremely different from case to case.
Yeah. This is for sure an issue in the sense that this is just an example on a patient. This is the brain tumor mask. What happened is that the brain tumor mask overlap with our gray matter segmentation a lot. And this is a problem in the parcellation in general, because we will have an overlap in the parcellation that we are using to construct our matrices. So what I was trying to do is to just remove this part of parcellation, as I was saying before, but this introduced a big bias because we are, there are some tumor which overlaps with the hubs region. So if I'm just removing this from the model, then I will have a different way of defining the hubs region. So what we were trying also to do is to better understand the overlap, the amount of overlap with the hubs region, and then try to better think about to include them as a predictor in our model. This could be a possibility. But also we know that, I didn't cite this type of analysis, but previously we were doing ICA on this type of data. And in our board signal, we weren't able to detect the component relevant for the tumor. So they were not, we cannot just like, let's say, quantitatively saying that they were not component of the tumor, but still the default mode and the frontoparietal network were assembling really, really nicely the atlas network. So yeah, this is a crucial thing, and we need to think about more about how to introduce this, but this introduces a bias for sure in the analysis. Yeah.
So do you hear me? Okay. So hi everybody, and thanks for being here. Today I'm going to talk about my ongoing PhD project, where we actually managed to map the network structure of the mouse-brain connectome with voxel resolution, so meaning free of parcellations. But why is working free of parcellation so important? The story starts here. I think that everybody in the room has already seen a picture like this. These are prototypical reconstruction of connectomes. Here for connectomes, I mean the complete description of the wiring diagram of the brain, as you actually get with MRI. We all know that MRI is quite handy to map brain structure because you can do it in vivo, so non-invasively, meaning that you don't have to kill your subject afterward, which is fine, I guess. And the other beautiful properties of MRI is that you actually can use it to map networks of brain structure across species. So here we have human, marmoset, and a mouse brain. However, we also, I think everybody in this room knows that MRI is associated with some important limitations. The very first one is spatial resolution. because as you know, these streamlines do not encode for a single axon. They encode for thousands and thousands of axons, meaning that we actually only can map the macro-scale organization of the brain. The other important limitation is, of course, the lack of directionality. So again, each of these streamlines encode for a bidirectional connection that has the same intensity in both directions. This is why the research field tried to come up with some alternative methods to probe structural connectivity. The gold standard here is of course, viral tracing. These are examples taken from the mouse brain. So viral tracing consists in injecting a virus in a specific brain regions, and actually this allows you to track structural connectivity as it propagates throughout the brain. And I hope that you can actually appreciate the spatial resolution, the spatial specificity we get when we zoom in some specific brain areas, as here, for example, in the basal ganglia of the mouse brain. Another very well-established fact, and actually this is why we talk about ground truth axonal connectons. And also here we are probing the mesoscale organization level of the brain, so, and not more the macroscale. So here, theoretically, here we could map what happens between single neurons. It is also very well acknowledged, actually, that the best structural mesoscale connectome available to date is the one of the mouse. And the reason why is shown here on your right. This is all work coming from the Allen Brain Institute, and actually their work allowed us to, for example, dissect the existence of functional circuits, so whose existence has been postulated for years, but actually never proved in such a network context. However, there are also problems with this beautiful data set, so namely people still use macroscopic parcellations. And why is this highly suboptimal? Because here we're assuming regional homogeneity. But just look at this parcellation, this is quite coarse. So, and I think that assuming that everything stays the same, for example, here, is actually at its best just naive. And in fact, using parcellation results in a coarse localization of network feature, and perhaps even more worse, it would potentially mask sub-regional attributes that are critical for the overall network. Luckily for me, especially luckily for me, the Allen Brain Institute had the same line of thinking about this issue, and actually very recently released a new version of this mouse mesoscale structural connectome. At this time with voxel resolution, so free of parcellation, and where we actually can map the connectivity between 500,000 of voxels. Which is so with this tool in our hand, we aimed at mapping the network structure of the mouse brain with voxel resolution, and in the process we also tried to address some important questions in the field, ranging from localizing central brain regions, so-called hubs, to probe hub function. We also were interested in mapping the hierarchical structure of the brain, and last but not least, we were also interested in probing the relationship between structure and function. So the very first question we addressed was quite simple. So where are the hubs of the mouse brain? For hubs, here I mean node with high connectional density, as shown here. And at this stage, we didn't take the directionality of the connections into account. This was sort of a proof of concept. And actually, our mapping revealed that hubs are mainly localized in higher order associative regions and in hippocampus. But perhaps what is even more important is that our fears were justified, because macroparcellation do indeed mask sub-regional features that are important for the overall network structure. Here, for example, the amygdala. This is only sub-part of the amygdala were classified as hubs, and not the amygdala as a whole, for example. And actually, this also confirms that we are indeed able to spot such sub-regional feature. So with this in our mind, we decided to map a much more interesting network property, which is the so-called network core, or also called rich club. It's shown actually here in red. The rich club actually probes the existence of, not only the existence of hubs, but also probes special patterns of hub-to-hub communication, because as you see here, hubs are also tightly interconnected to each other. And the rich club has been shown to be very important because it is a crucial integration point in the network dynamics. This has been shown also, for example, in human studies. So when we map the the rich club of the map brain with our voxel distribution, we found that it actually clusters along two functional axes. The first one is the so-called lateral axis. This is a major pathway of the mouse brain. And the second is the so-called frontothalamic, mid-thalamic hippocampal axis, which is very important for complex behavior and learning, for example. And additionally, and this is also something very exciting, at least for us, for the first time we report the involvement of neuromodulatory ascending nuclei as being part of this rich core. Here we have the VTA, which stands for dopamine. So, as I said in the beginning, here we didn't take the directionality of the connections into account, and now we actually tried explicitly to do so. So here we just ask ourselves, okay, by incorporating the directionality information, do we gain some important insights into how the brain is organized? To do that, we mapped so-called source and sink hubs. Source hubs are nodes or brain regions that actually are characterized by having many outgoing connections, and sink hubs are brain regions that are characterized by having many incoming connections, and in a sort of, so to say, master-slave relationship. And mapping source hubs actually revealed that dominating brain regions are localized in higher order associative areas, whereas at the bottom of this novel established hierarchy we have the basal ganglia, which are important for motor output. And actually extending this approach to the whole brain revealed that this hierarchy is actually there. And this is important because, in our opinion, it defines a new organizational axis of the mammalian connectome that has never been reported before. But still, hub mapping doesn't tell us anything about the existence of, so to say, functional subunits. We all intuitively know that, for example, the auditory and the visual system have a precise function, and that we also know that they are densely interconnected to each other. And these sort of functional subunits in graph theory jargon are called modules or community. So here we mapped our communities, our structural communities, and here we found something that is, again, is super interesting, because by applying the same methods to functional fMRI data, we found an incredible spatial overlapping between structural and functional community. And why is this so important? So I just ask you to follow me 1 minute more. Because this actually allowed us to map another set of important brain regions that are called hubs, which are called connector hubs. And as you see from this toy network, they are important because they mediate the communication between networks. They are sort of local integration points. And when we actually map them in our connectome, in our structural connectome, with our huge surprise, we found them to be localized within the major neuromodulatory system, so where dopamine, serotonin, and noradrenaline is produced. And why is this now so important with the functional communities? Because we have seen that they overlap quite well. We see that structural connector hubs are localized within the major neuromodulatory system. So this actually raised the concrete hypothesis that structural connector hubs also drive functional interaction between networks. And spoiler, we actually know that this is the case, because if you stimulate the locus ceruleus, so where noradrenaline is produced and released, what you see is that a rapid reconfiguration of all the major functional systems of the brain, both in human, macaque, and also in the mouse. This set of results, together with the fact that we have this sort of ground truth connectome with unprecedented spatial resolution and the directionality encoded in it, prompted us to ask ourselves another, actually, it is also another long-standing questions in the field. So, what is the role of hub regions? So here I just showed you a possible biological function. So, but now, how do they shape the network topology? Graph theory, from which actually hubs are derived from, postulates that hubs are critical for maintaining network integrity. What do I mean here? So again, we just look at this toy network. So the hub is clearly here. You see, it takes these four sort of communities together. So if we were to perform what in this technical jargon is called targeted attack here, what we have is network fragmentation. And this is indeed very bad because these pieces cannot talk to anymore, and this actually means network breakdown. So this actually was also the very first feature that we tested in our data. Here, on the left, we performed this hub removal, and we indeed see that network integrity decreases. But with our huge surprise, we also saw that the target hub removal is actually the same as random node removal, which goes against all postulates of graph theory. But at the same time, it's also fascinating because it actually highlights the resilience of the mesoscale structural connectome of this species. We then try to map another important network feature, which is a network efficiency. And again, the effect of targeted hub removal was more or less the same as random node removal. And here again, so the question is still there. So what are hubs for? Do we really have hubs, or they are just, I don't know, statistical artifacts? And at the end, indeed, we found what hubs are critical for, and this is called network communicability, which, very roughly speaking, is a measure of the network broadcasting capacity. So the capacity of the network to spread information around its members. And guess what? Connector hubs were actually the most critical in reducing this metric. Again, highlighting that connector hubs are essential for both between network communication and also for the overall communication capacity of the network. In the very, before concluding, on the very last two slides that I have left, I would also like to talk about hierarchy, so because it's the last point that was left out. And so far we have talked about hierarchy in quite rough terms, because we just say, okay, hub, non-hub, we delete. But what is missing is now a network perspective. Methods to map such hierarchy actually exist, have been applied in the human brain for the first time. Actually, I will save you all the technical details, but the most striking results here, so the take-home message is that the intrinsic brain organization, at least for humans, can be the most salient feature describing the network architecture of the human brain is this contraposition between polymodal brain region, so the default network, and primary sensory cortex. And here for contraposition, I mean just the spatial arrangement of connectivity. So on the one hand, we have the default network, and on the other hand, we have unimodal sensory cortices. And perhaps even more interesting, this structure, this organizational principle has been shown for the macaque monkeys as well. So actually raising the hypothesis that here we are in the presence of sort of evolutionarily preserved architectural principle of brain organization. And actually, we ask ourselves, okay, is this the case for the mouse as well? And we use the same methods, and indeed, yes, we found again a similar spatial structure. So highlighting that maybe for real, this is evolutionarily preserved architectural principle guiding brain organization. And it's also important because it has been shown that this organization is totally deranged in autism spectrum disorders. And this actually highlights the potential of using mice as a tool for studying, again, neuropsychiatric disorders. Last but not least, we were also interested in mapping a correspondence in this hierarchical structure between structure and function. And again, we found a close correspondence. So just look here, these two maps are almost the same. And this is, in my opinion, something a bit more important than just probing a spatial overlapping between networks, because this actually what says is that the intrinsic organization of structure and function is very similar. With this, I'm done. So I think we can safely skip the conclusion. I would just like to highlight that we are wrapping up everything in a paper, so I think it will be out at least in my archive in the very next week. So if you are interested, please read it and give us feedback. So thank you for your attention. I would also like to thank you all the lab members, collaborators, and last but not least also the Allen Brain Institute who collected the data and make them publicly available. Yeah, I mean.
Do you hear me? Yes? Okay. While I'm preparing this, I just want to say, last time I was here with Ludovico. Totally a different scenario. Okay, where are my slides? Okay. Hello, everybody. Thank you for coming. Today, I'm going to present you the work I've been doing in the past year, named Lucus Aurelius Ensemble-Based Modulation of Cortical Rhythms. Okay, let's start by first introducing the LC and stating that where it is. So Lucus Aurelius is a group of neuroepinephrine projecting neurons that projects broadly to the areas of brain and has been evolutionarily preserved across many species. Given its broad projections to the areas of our brain, it's no surprise that it's involved in many cognitive functions, such as wakefulness. So low levels of neuroepinephrine has been associated with sleep-like states, whereas high neuroepinephrine has been associated to more awake states. Also, LC and neuroepinephrine has been involved in sensory gating, shifting attention, orienting reflex, as, for example, this study shows that the mouse changes its attention toward many stimulus in the situation during drug self-administration. Also, it's involved in anxiety, stress response, fear conditioning, fear extinction, pain, and analgesia. However, a long-standing question about the function of Lucus Aurelius is that how can one tiny module affect all these aspects without affecting the other ones? For example, norepinephrine activation enhances perception of visual and auditory stimuli, but it also diminishes the perception of nociceptive stimuli. Again, norepinephrine activation promotes fear conditioning, but paradoxically also promotes fear extinction. So how can one brain structure modulate incompatible functions altogether? One emerging perspective regarding the role of LC is that it works in a smaller module, each associated with a specific function. For example, you can have a prefrontal projecting module that can affect aversion and anxiety, and the spinal projecting module for analgesia. Also, you can again have a prefrontal projecting module for fear extinction and an amygdala projecting module for fear conditioning. So to give you a summary, I introduced ULC, I talked about its role, I brought a question about its function and give a possible solution. So what's the problem? Let's go home, right? But there is always a but, is that for so long it's been believed that LC units all fire synchrony together. And in order to have specific modules, I mean, this is impossible. If you have all the units fire synchron together, how can you have modules? However, most studies that investigated the Lucus Aurelius and came out with this synchronous firing use single electrode recordings, which allows you to have at most up to 2 or maximum 3 single units recorded at the same time, which makes the possibility of analyzing synchronous firing almost impossible. Here, our collaborators at the Max Planck Institute in Tübingen managed to use highly dense, compact electrodes and managed to record for the first time a large-scale data from LC, 20 units on average for 12 rats, which was later on extended to 15, allowing to investigate 3,164 unit pairs under urethane anesthesia during a spontaneous activity. The early results first showed very low spontaneous correlation between the LC units. I mean, up to 87% of the units did not show any significant correlation with each other. More importantly, they were able to find two different cell units based on the spike shapes, which they called narrow and wide units, where the narrow units were mostly localized in the ventral part of the LC. So this paves the way for us to deep in and investigate the so-called ensemble-based coding, because as we can see, they are not synchronous together, so they can be able to have some sort of ensemble coding. To detect the ensembles, we use the non-negative matrix factorization. Just allow me to very briefly show you how it works. Imagine you have this hypothetical spike recording of 15 single units. As you can see, for example, units 11 to 15 tend to increase their firing rates altogether, right? So if you apply the NMF to this data, you end up with two matrices. The first matrix associates units to different ensembles. For example, here you can see that the ensemble 1 is mainly consisted of units 11 to 15. And it also gives you another matrix which shows how the activity of these ensembles resolves over time. So during which time the ensembles are active, not active, etc. So here you can see, for example, the ensemble 1, the so-called activity pattern, tend to increase during the times that there are synchronous firing. So when you do this sort of analysis and pull the spike rate of the LC single units, you end up with something like this. So you can see that the whole activity is being dissolved to many ensembles that can, at times, fire synchronous together, but at the other times, they have very sparse and different firing patterns. So also, for example, here you can see an ensemble made of 3 units. Aligned to the ensemble activation time, you can see that the units that fall into the ensemble tend to increase their firing rate aligned with the ensemble activation, whereas the units outside the ensemble tend to keep their activity more or less constant. So having this tool, we can also investigate the properties of the so-called attained ensembles. The first thing is the spatial properties, whether the ensembles are made of the same amount of neurons, the same amount of percentage of recording units. No, we find very, very different ensembles. Up to 60% of the whole neurons recorded could fall into the ensemble, also as low as 10%. The next thing was the temporal properties of the ensembles. At the very least, we observed that if we cluster the so-called PETH due to the ensemble activation, we can cluster them into 3 groups of low increased firing rate, medium increased firing rate, and high increased firing rates. Again, interestingly, we found that most of the ensembles are made of the same cell types, meaning that the wide units tend to group together. Also, narrow units tend to group together. Another thing we investigated, which was rather obvious, was that the neurons in the ensemble, the single units into ensemble, tend to go into the periods of burst firing more often during the ensemble active times rather than their inactive times. Also, having time resolve the activity of the ensembles made us to analyze their interaction with each other, which resulted in very interesting patterns of auto-inhibition and self-inhibition at the specific peaks. For example, we observed that the ensembles tend to inhibit each other, inhibit themselves at the peak of 100 milliseconds, decaying and then failing to show any significant pattern of inhibition after 400 milliseconds, whereas they tend to inhibit each other with the peak around 300 milliseconds, which is associated to some sort of lateral inhibition due to GABA release and some other biological things. Okay, so at this part of the talk, I talked about the observed low synchrony. I talked about the ensemble detection using the NMF and their properties. Next step is that we were interested was that whether the ensembles are capable of modulating cortical rhythms differently or not. So we did so by triggering the prefrontal cortex LFP power spectrum on the LC ensemble activations for the animals that we had simultaneously recorded the LC and the LFP of prefrontal cortex. Clustering them with k-means revealed 4 different types of neuromodulations, type 1, 2, 3, 4. We also observed that these different in these 4 types is not due to any intrinsic properties of the ensemble. For example, now nothing changes significantly in terms of number of neurons in the ensemble, their PETH, their spike rate, nothing. So we can at the very least say that the neuromodulation patterns are diverse, and the type of PFC activity actually depends on which ensembles are activated. So having assessed the significance of the changes in the prefrontal cortex change in power spectrum, we find that the 3 type of neuromodulation effect happens after the ensemble activation by the means of, in type 1, decreasing low frequency, while increasing mid to high frequencies. Type 2, very significant increase in the mid frequency. And the type 3 that just decreases from mid frequency up to high frequencies. And one set of the LC triggered modulation shows the significant change both before and after the ensemble activation. So it first starts by an increase in mid frequencies up to high, and then followed by a decrease in that specific frequencies. So I want to conclude by saying that we investigated the idea of synchrony versus ensemble firing in the LC. We observed very low synchrony among LC units, which paved the way for us to detect the LC ensembles, which are mainly made of the same units. Having resolved the ensemble's activity over time, showed different temporal properties and allowed us to investigate the interactions among ensembles. We also dig into the possibility of global versus target-specific projections, and we saw that the LC ensembles are actually capable of differentially modulating cortical rhythms, and this is not due to intrinsic properties of ensembles like number of neurons or their firing pattern, etc., etc. I want to close by stating that LC could still be capable of sending general arousal signals by the means of having all the ensembles synchronous firing, so this is still possible. But at the same time, it can have target-specific and information-specific modules, having just the specific ensembles that project to a specific area of a brain active. So in the end, I want to thank to my PI, Professor Panzeri, Dr. Nelson Tota, our collaborator, for a lot of biological feedback, my amazing colleagues at the Neural Computation Lab for tolerating me. Okay, we started funny, but at the end, I want to dedicate a moment in the memory of all the victims of the Ukraine international flight. Well, most of them were scholars like us, so I think at least it deserves attention. Thank you very much. On the microphone.
So it's quite a naive question, but the animals were anesthetized, right?
Sorry?
Were the animals anesthetized when the recordings were made?
Yes,
If the locus coeruleus is like much less active when the animal is not aroused, how would that affect the synchrony? Might there be more synchrony if the animal's like awake, alert, and moving, and this region's more active?
Yes, that's the first question I get every time I present this, because it's true that the urethane decreases the activity of LC, so it can decrease the synchrony for sure. But the thing is that let's assume that the anesthesia has a general role in just decreasing the firing rate. But is it really possible for anesthesia to dissolve the one module into specific, like certain modules? That's a little bit unlikely. And in the first study that they investigated the synchrony, they also did some foot shocks to trigger the LC and see whether the stimulus triggering would increase the synchrony. So when the LC is engaged in some cognitive function, will it increase its synchrony? No, the result was still, even during the stimulus, the synchrony among the units is super low. But I see the point that the ensembles that I found here are only valid for during the anesthesia. So also their properties, whatever, is only valid for anesthesia. During awake states, we don't know. At the moment, they are trying to collect the same data set, but for awake animals. So we should wait and see how it pops out.
Which is the contribution of excitatory versus inhibitory neurons to population responses in the locus coeruleus? And do you plan to investigate these aspects as well?
Well, I don't know. I discussed this with Nelson. I don't know how we can really put excitatory and inhibitory label in the LC. I mean, usually in the cortex, you say narrow and wide, and one of them is excitatory, the other is inhibitory, right? Here, we cannot say this because we don't know. It's the first time that these different unit types are found. But what we found was that actually we found that the narrow units actually tend to spike more often. So they could be somehow related to fast spiking neurons that we say in the cortex, but nothing concrete, nothing. So let's just for the moment call them wide and narrow and not put any label on them.
So thanks to the three speakers, it was really, really nice. I would just now like you to invite you to go to the poster sections downstairs. So there will be first the second and then the third PhD students presenting their posters, and then there will be also the first years presenting, and there will be a coffee break. And then we can all meet around here to see who won the prizes for the best talk and the best poster. Thank you.
So, we are back from a very interesting and eventful poster session downstairs. And we have the winners of the talks and the presentations. This is a little, it's not really a great sum, but it's something that the doctoral program puts aside for the PhD students. It does not come from your personal endowments. So there is a money reward for the best posters and best talk. And the Professor Bozzi is here to to hold the list up so I can, well, but the handshake will come from the professor, not from the administrator. Ecco. So we'll start from the third prize, which is actually a tie, and it will go to both Dr. Anastasia Morandi-Raikova and Dr. Claudio Greco. And Claudio Greco. Thank you. You come to my office tomorrow. Second best poster goes to Federico Rocchi.
Not that fast.
And last but not least, best talk goes to Shari Arnoy. Sulla valutazione della commissione.
Okay. Well, just a quick words about the evaluation. And regarding the poster, well, I don't remember how many evaluators we were, something like 7 or 8. So, I mean, quite a big group of us. We evaluated the overall structure of the poster, the clarity in presentation, the clarity in exposing the aims of the study, the results, the methods, the visual composition of the posters, and that's basically this. And regarding the talks, well, of course, we tried to we evaluated how the presenter was proposing the major aims of the study, and also in the case of the presentation, the overall structure and visual appearance of the slides, the clarity in exposing the methods, the results, and also, I mean, in theory, we should have evaluated the answers to the questions. But unfortunately, one of the presenters was not asked any questions. So that parameters, how the students replied to the question, was not taken into consideration. In any case, this is the evaluation, of course, is the sum of our 7, 8 different scores that we give to each of the students. And we are pretty much sure that we chose very, very, very valuable talks and posters, but the evaluation was extremely difficult because the level generally was extremely high, and this is what we really liked about this afternoon. So thank you all for your work and for your passion in what you're doing. So thanks a lot.
Just out of curiosity, who was in the evaluation committee? It was Professor Bozzi, and can we say who the other committee members were?
I remember some of them. I'm sorry, not all of them. I remember Tettamanti, Bottini, Viganò, Uwe Meyer, Simona Monaco, Moritz, Marie Ebert. I'm sorry.
So thank you, actually, for doing all this.
Okay, thanks a lot.
Okay. So with that, I'd like to welcome. Okay. Vittorio Iacovella, who's our speaker today, and I'm so proud to say an alumni of the PhD program himself from the 24th cycle. So, well, we don't have to say how many, we don't have to do the math right now. So, but you're here for the Open Science Seminar for this month. And with that, I'll pass the phone. Actually, you'll go from there.
Ok, così stile Trump? Da qui? Ok. Can you hear me? Oh, questo è acceso? No, ok. Ok, so, hello all. Welcome to the first Open Science Seminar for 2020. I just want to thank Lea Mercanti for this wonderful presentation. I have to say, yes, this is the place where I received officially my PhD back in 2013, and that's actually the first time that I present something related to science here. So that's very, it's a big deal. I mean, being here. Whatever. Let's see whether this works. Okay. So first Open Science Seminar for 2020. Let's take a look of what we did in 2019. For those of you who are new in this place, we start these seminars. They are actually part of this Think Open at CIMEC initiative, which is the open science initiative within Center of Mind and Brain Sciences. We plan to do up to 5 or 6 seminars per year. And last year we started in February with Folco Panizza, which is actually a PhD student here, talking about register reports. Then we went on with Matteo Caffini in May. He talked about how to reach data fusion in an open research environment, and he specifically focused on the near-infrared spectroscopy case. On May and in November, I talked about open access for open science, and I focused first on general aspects of this topic, and then I specifically focused my attention on communicating online your research products in an open access environment. And then in November and December, we had 2 guest speakers, Professor Perugini and Professor Grassi. They talked about replication, replicability crisis, and how to deal with these problems in an open science environment. We covered lots of these kind of like semantic aspects we used to mention every time we present something at the Open Science Seminar: preparation, discovery, analysis, and so on and so forth. Open access for open science. This specific talk, which is similar to those 2 I gave last year, but don't worry, for those of you that already attended those talks, I integrated lots of concepts. This is not redundant, and it's also related to publication and outreach as well. We will start by introducing the topic, and then we will focus to a specific way to go open, which is the green road. And then at the end, let's say this first part, even for those of you who are still not interested in for example, research evaluation, talking about, for example, master students or PhD students, maybe you're not interested in, let's say, research evaluation and so on. This first part, it's pretty generic, and it's really useful to get, let's say, the flavor of this discussion which is going on since a long time. And then the last part is specifically dedicated to a tool which is institutional research information system, IRIS. I think all the people dealing with the evaluation of their research, they already know this tool, and I will give a very quick how to complete or integrate your research products on IRIS in order to make them visible and evaluable by formal, let's say, government institution and funding institution. We are talking about giving free and immediate access to research products. This is what open access is about. This topic, it's not new, and it's not even recent. In 1991, a few physicists in US, they start putting, let's say, versions of their papers before submitting them to a subscription journal in an online archive. This initiative developed until they gave the name archive, and unsurprisingly, this is an archive of preprints. 1991, so it's almost 30 years ago. I bet that many people in this room, they were not even born at that time. So this is not a recent topic. I just want to mention 1997, the initiative by physicists, usual suspects, in Sista, Trieste. This is the first initiative in Europe, say the first attempt to create an online archive, which developed at that point that they create an actual online journal. You have to think about the time, like 1997. At that time, the web was not that developed and so on. Many scientists, they used to have, like, all the institutions, they used to have these physical archives, so papers. I mean, papers in paper, not in an electronic form. Maybe some of you remember those kind of cabinets with sort of like slides and taking like these journals and making copies and so on and so forth. And that time, in Trieste, they decided to create an electronic journal. And nowadays, this is one of the most, journal of high energy physics, this is one of the most significant experiences ever in science. So let's say that during the 90s, like many other things, all these kind of like thoughts were boiling over until the point that in 2003, scientists decided to gather and let's say develop or write down a proper declaration, which is called Berlin Declaration because it was made in Berlin. And this is like the pillar of, it's very brief, it's very quick, we are going to read it in a few seconds. And it's the formal definition of what open access should be. What is actually recent, this is something that that could interest, let's say, professors and other, let's say, people dealing with research evaluation. So in 2019, a few weeks ago, Italian institutions, they stated that research products that are going to be evaluated should be freely accessible by everyone, and they should be deposited in an online repository, for example, an institutional repository maintained by your institution, an open subject repository, for example, archive, and so on and so forth. So this is a a topic that nowadays it's something that is kind of mandatory to be at least discussed among scientists. The premises of Berlin Declaration 2003 were that sources of knowledge and cultural heritage approved by the scientific community, they should be readily and widely available to society. This is sort of like political statement that says that knowledge should be for everyone. And internet, in their vision, should be seen as a functional medium to distribute knowledge. I know that in these days where social media are, let's say, source of fake news and many other distortion, but in the intention of people writing down the Berlin Declaration, internet was something that would be useful to spread knowledge. And knowledge includes, for example, scientific research, which is the topic that may be interesting for us, raw data, metadata, source material, and then other stuff like pictorial and graphical material and so on. Berlin Declaration, let's read it together. It's very quick, very brief, very concise, but it's dense, and it actually opens many kind of, let's say, other lead to many other consequences. It's two statements. The first one related to authors' intents. So authors and potential right holders of a contribution, they grant free, irrevocable, worldwide right of access to their work. And this part is just a declaration of intent. It requires authors and right holders just to think about granting access to their intellectual product. In this part of the Berlin Declaration, there is no, like neither editorial or practical implication. We are not talking about like double dipping, publication fees, article processing charges. It's just a declaration of intents, how you think about your research product and the destination of your research product. But of course, there is the pars construens, the second part, action needed. A complete version of the work is deposited and therefore published in at least one online repository which is maintained by an organization supporting open access. This is one of the most relevant parts of this declaration. So you should take a complete version of your work and upload it somewhere. Where? In an online repository which is maintained by someone which is supporting open access, not someone that wants to make money with your research product. And the way in which an author implements this statement defines whether and how the piece of work is available or not in an open access form. This statement, I think it's really interesting because it's inclusive. It doesn't rule out any specific possibility for the authors to deposit the paper. In this statement, they didn't write down, they didn't rule out the fact that you can deposit the paper somewhere and then submit it to a subscription journal. It excludes commercial initiatives, though. And we are going to mention a few commercial initiatives later on. And here, the role of journal editors, it's kind of like shaping up because it determines how a work, let's say, the way in which the work will be considered and the way in which you will be going open. So that was a sort of introduction. So it's not a recent topic. There is a formal declaration which gives somehow practical direction of how to go open. And then here in the second part, I will illustrate quickly the way in which today we consider, let's say, relevant to go open. There are two equivalent roads. One road which is called the green road, which is the self-archiving way, and it's the way we are going to describe in details today. And then there is the gold road, which include the open access journals, with article processing charges plus, let's say. So those journals where you don't have to have a subscription, you can read the research product published in those journals. Everyone could read the contributions on those journals, but you have to pay to publish there. I have to say that here I'm not considering, let's say, a specific or a particular way to go open, which is very popular nowadays, which is, someone define it the red road, someone they on purpose exclude this way because it's not really, let's say, a way to go open, which is when you publish your paper on a subscription journal, and that subscription journal, it offers you a paid open access option. This is very popular. But still, bottom line of this procedure is that you're going to pay the subscription to the journal and the open access option. So you're going to pay twice to obtain the result of going open. A result that you could almost always obtain with the green road. As a matter of fact, it's the way we're going to describe today. This way, it's always free of charges. It's approved by, for example, MUR for research evaluation. It's simple to finalize using, for example, Unity and tools. The problem with this option, or let's say the byproduct, is that, for example, it suffers conditions imposed by the publishers, for example, the embargo periods. But this is something that almost always refer just to the final version of your paper. The directions to go open in the green way are the following. So you have your paper, let's say the version of the paper you're going to submit to a subscription journal. So with this paper, with this version of the paper in your hands, you're going to submit and eventually publish your work in a subscription journal. At the same time, you're going to take your preprint or submitted version and deposit it in an open access repository. And that's it. You went open. You can present your work as open access for your funding agency, for a research evaluation agency, and so on and so forth. And also, your work, which is going to be, of course, peer-reviewed from a journal, it's already there, and it's already there online. It's visible, it can be discussed, you can already get feedback, and you have already, let's say, a recipient that you can present, for example, in conference and so on, and people can point to an already static place where your work is. There are many online tools to check what you could do on how you should go green. One of the most interesting tool, in my opinion, is this Sherpa Romeo tool. You just go there, write down the journal you want to, the journal you pick for your submission, for example, neuroimage. And this is sort of Google for journals. It will return lots of features related to the open access discussion, related to the journal. And here, I thought that it was relevant to report this journal because, okay, this is actually the current situation. So, if you submit your paper in neuroimage, you can archive preprint, so you can go green. You can go open the green way. You can archive the post-print, which is the final draft post-reviewing, let's say. And you can also archive publisher version PDF. That's like the definition of an open access journal. And this is because neuroimage, right now in 2020, it began an open access journal. For example, last year I have this screenshot from my talk in May. Last year, NeuroImage was not an open access journal. As a matter of fact, you could not archive publisher version PDF. And that's, let's say, an evolution of what you could do with this journal. Either way, you could always, last year as well, you could archive the post-print, so the final draft post-reviewing version. So it's not really a big, I mean, it's a big change, but from, let's say, the open access point of view, it's not like a huge change. And for example, other journals, for example, Neuron, Sherpa Romeo gives you already a glance of what you could do and not do. For example, if you want to submit your paper in Neuron, then you already know that you could archive preprint, and you cannot ever archive publisher version or PDF, so the formatted article, and you could archive the post-print, so the version of the paper after the reviewing, just 12 months after the paper is published. So that's the point, or let's say that's the problem of going green. Embargoes and so on. So after you have your paper and you Google around which journal you want to consider and so on and so forth, you have to choose an online repository to deposit your paper. Archive, already introduced it. It's a very famous preprint archive. Nowadays, since 2013, there is this online initiative. It's called bioRxiv. It's maintained by Cold Spring Harbor Laboratory. I'm reporting this because this is an online resource which is maintained by an open access enthusiast, let's say, initiative, which is Cold Spring Harbor Laboratory. This is slowly establishing itself as one of the standards in the field. It can contain full papers. It gives you a digital object identifier, a DOI, which is a permanent link to your paper. You can update your deposits there, and you have the history of your updates. It takes comments. It has social media, let's say, flavor, in the sense that if you tweet about this paper, then you will see under the paper who tweeted that, what they are talking about when they share the DOI, and so on. Well, what I just want to point out is that maybe, I hope not many of you, but some of you could think about uploading their work in academia-oriented social network because they look captivating, they're easy to use, they do lots of stuff like in an automatic way. You just type your name, and 10 seconds later, you have your website with your photo, all your papers, and so on. I'm talking about ResearchGate, academia.edu, and so on. They also offer a paper hosting service, which seems to be similar to Green Road Deposit. And you can think about, let's say you can think, okay, my papers, they are on ResearchGate. They are online, preprint, for example. I have my link to the paper, there is the description, there is my photo, all my science is there. So I already have a version of my papers deposited online. But this is not open access. Just remember the Berlin Declaration, part 2. These online archives, they are not maintained by an open access enthusiast initiative. They are commercial initiatives. So they could cease to exist, they could change conditions, all of a sudden they could sell all your stuff, all your data to someone else, and so on. So I'm not saying that you don't have to just do whatever you want. I mean, I'm just saying that this is not an official way to go open. So if someone says, did you go open? Yes, I deposited my work on ResearchGate, you didn't go open. So let's switch. I think I actually finished the part of what is the green road, how to go green, how to not go green, and so on. Let's just switch to the last part of the talk, which is related to going green by using Iris. Because there are many initiatives let's say, related to, there are many online open access archives coming from many different institutions. Let's say bioRxiv, we already mentioned that, Zenodo, OSF by Center of Open Science, SciArchive, and so on and so on and so forth. Each of them, it carries pros and cons, and you can, let's say, kind of proliferate the copies of your papers in all these archives and have them disseminated online in many places. What is very common for almost all the institutions related to research is that there is already an archive which is maintained by the institution itself. And most of the time, as you part of that institution, you are required to maintain the list of your research products on that archive. And this most of the time is crucial for research evaluation and funding. That's the case for UniTN as well. As a matter of fact, UniTN, it has this institutional research information system, which is developed by CINEGA, which is another Italian institution. There is an entire office dedicated not only to IRIS, but to many aspects of scientific publications within UniTN, which is called Scientific Publication Office. And this archive, it's, I'm not going to sell this to you, but I have to say that it's a very interesting archive because it carries many capabilities. Open access is one of these, but also shared Romeo integration. So this means that those Googling around to see what are the open access capabilities of a journal, it's already integrated in this tool. It has this OAI PMH, it's not a bad word. This means that an archive that has these capabilities, this means that the search engines, let's say Google Scholar, they are facilitated to grab information from this article by construction, let's say. You could go open, let's say you maintain your own website, drsmith/sites.google.com, and you put your papers or preprints on your website. That's totally fine. I mean, it's something which is allowed also by the research evaluation procedure. The point here is that your website is very unlikely to have these OAI PMH capabilities. So, for example, Google Scholar won't automatically recognize the fact that on your website there is your paper, or there is a version of your paper which is a scientific paper. If you put, on the other hand, your paper on such an archive, for example, IRIS, Google Scholar is going to automatically recognize that there is your scientific paper, which has scientific content and so on and so forth. And also, this is going to grab lots of metadata, which is, in some sense, as relevant as the data for some reasons. And also, and we discussed about this last November, it has rich, highly integrated, and dynamically update altmetrics. Talking about altmetrics is not the purpose of this talk, but I just want to say that in this specific moment, having, let's say, dealing with altmetrics could be not as important, but it's something that is going to complement the classic bibliometrics measures. Altmetrics is something that refers to how many times your paper is visualized, how many times your paper is downloaded, how many people they are talking about that on Twitter or on other social networks, how many popular science journals are talking about your paper, and so on and so forth. So this is something that refers to, let's say, the general impact of your paper with respect to the scientific impact. It's like the buzz your paper is going to generate online. And it's something, I mean, it's from a scientific point of view, I know for sure that it's not as important, or it has a different kind of importance with respect to bibliometrics, but it still has its significance. And this is mandatory for Italian or European research evaluation. You put your stuff on IRIS, and then it's going to be validated and evaluated by funding institution. The interesting part of the story, especially here in Trento, is that there are supervised sanity checks. So people, they are going to check what you put there and see whether there are missing metadata, if you were wrong in including one author with respect to another, and so on and so forth. This is the last part. It's sort of like a quick how-to use IRIS for going open. So this is dedicated especially to people that have already records on IRIS. As part of UniTN, you already have an account on IRIS. You can connect to IRIS, iris.unitn.it, and you will be presented with a list of the stock products. These are your papers you uploaded or recorded throughout the years. Just pick a paper, and you will be presented with a screen with lots of metadata. For example, the journal, date of publication, the DOI, and so on and so forth. To go open, just click on Complete Submission here. When you click to Complete Submission, you will be presented with a sort of like paper metadata revision. So, for example, the kind of article, the title, the year of publication, and so on. This is most of the time already generated automatically by the system. And then there is the upload screen. In this upload screen, you are requested to submit a file. What I want to stress for you in this specific part of the talk is that there is here on the right Sherpa Rome integration. So here I have the list of what I could do and what I should not do according to the journal policies with respect to the open access. This is something like, you know, a way to save time or a way to be sure in an automatic way, be sure of what I could do and what I cannot do. Because here, this paper was published in Magnetic Resonance Imaging Journal, and in that paper, I could archive the preprint, I could archive a postprint, I cannot archive publisher version. So if I'm going to upload the publisher version, I'm like I was already warned that I could not. Of course, then, because of the way in which IRIS works, I will have a supervised check, and it's very likely that the administration would say, you cannot do that. But still, here I have already like this kind of summary which reminds me what I could not do. And then I would just upload my file and select the type of material I'm going to include in my record. Here there is a list. If I'm going to upload an abstract, other material, for example, supplementary material, or whatever. And then I have the list of exactly what we initiated, what we mentioned before. For example, the referral postprint, the preprint, For example, if you're dealing with very strict, with journals with very strict policies, or for example, the editorial version, the case of neuroimage, or whatever, doctoral thesis, for example. And then there is also this kind of access policy. According to what you could upload related to what the right box suggests. For example, suppose that I uploaded the postprint. I'm allowed to do that. And then I click open access, and I went open. And that's it. I can finalize the submission with verify. I will undergo a sanity check by the administration, but my research output is open access, and therefore is valuable by the, it could be considered for evaluation by evaluation agencies. Here there is also the option of uploading something which is subject to an embargo. So I upload today, for example, the author postprint version. I specify the date when the embargo will finish, and I'm already done. Once the embargo is finished, I went open. And that's, I mean, a very handy way to be, let's say, coherent with the journal policies and just to skip all the, like, coming back when the embargo finishes and so on and so forth. That's just because I want to upload the postprint, for example, but if I archive the preprint, I went open and there is no embargo. So once you completed the step, the research product will be checked for metadata coherence by the administration, and your product will be open access. The interesting part of the story is that IRIS is very dynamic because you could always update your research product by following exactly the same steps. Suppose that, for example, all of a sudden the policy of the journal changed, like in neuroimage case, from, let's say, a paid option journal, it become an open access journal. Then what you want to do is to put on IRIS the final version, for example, the formatted version. Just go there, follow the step, upload the final version, you went open, and you have your updated research product. So, just a quick recap. Going open, the green road, it's free of charge, it's safe, there are rich institutional resources available, it's compliant with the research evaluation system. This is an article, this is, let's say, one of the articles of the Italian law, and at the point A, it's explicitly mention institutional repositories. So if you want to be compliant with this law and you want to use IRIS, that's the way, and you're fine. I just want to say a very quick, let's say, a very quick different word with respect to what we said so far. This recent law, I think December 2019, it includes lots of many new concepts. Open access is one of these. The other interesting concept is that this law specifically mentions research products, not only papers. This means that for Italian law and for evaluation purposes, they are going to consider both publications, let's say scientific papers, but also other scientific products. For example, protocols, open data repositories, and so on. This is it may seem just like a formal or technical step, but this is actually a very interesting change of the approach by the Italian law to the way in which they think a researcher life is, let's say, about. It's not only, nowadays, it's not about publication or scientific papers anymore. It also includes other products. This is something that follows, let's say, in the US, the National Science Foundation, the NSF, they made this, let's say, huge step back in 2013. So after 6 years, Italian law also, they actually included this part, and I think it's really relevant. And that's it. I hope that this was not too technical. And I hope that especially the first part was of interest also for the students and the PhD students. And I think I'm open for questions and other discussions.
Thank you very much. I have just one question, because you mentioned among the open repository, PubMed. But any time I try to look for something in PubMed, it says that I have not access. So how can one have access to PubMed? Yes, I cannot have for free the system always asks me for a login name or something like that, and he asks me to look if I am in an organization which is allowed to access PubMed or whatever.
I'd say that PubMed initiative, it's a bit of a complex animal, let's say. I think that it has like, it's PubMed, let's say, paper search engine, and also PubMed Central, which is actually an open access archive. I think that this PubMed Central archive is subject to journal policies restrictions, so it's not mandatory that if a paper is on you can see a paper on PubMed, it's not mandatory that this paper is open access. If it's open access, though, you can find it on PubMed Central. So I think it's not an online archive. I don't know. It's not an online repository for open access. So I don't know. Yeah, okay, yeah, so the Italian law. So in that case, I think they are thinking about this PubMed Central online repository, which is sort of like a PubMed capability to deposit the paper which are already open access there. And for them, I think, okay, now I understood. I think the flavor of this kind of mentioning PubMed there is that if somehow your paper is open access, and even if you don't know anything about open access and whatever, chances are that your paper is already there, already openly accessible, so you don't have to worry to, for example, upload it on Iris or whatever. It's already there. And they are saying, if it's there, for us it's fine. This is the flavor. But if it's not there, then it's your duty to, if you want that paper, because I'm not an expert, I'm not going to do research evaluation myself, but I think every researcher should put 5 products, I think. Or I don't know, I don't want to say, let's say, false sticks, but I think you're going to select the papers you want to be considered for the evaluation. So if that paper, which is not open, you want it to be considered for the evaluation, then you have to do something to make it open. And for example, this using Iris, which is mandatory for other evaluations or for evaluations in general, it's a way to give an open access flavor to you to the product you want the evaluation initiative to consider. Other questions?
Thank you for the talk. I have a question about the gold open access. When you publish, for example, in eLife or some other journals, they have actually to put them also on archive. So if you take eLife, they put everything on GitHub. And my question is then, what's the advantage to put it yourself on Iris or something else? Does it give you more visibility, or what's actually the advantages? Because commercial publishers are supposed to do that.
Well, I don't know like all the features of eLife, but do you have like article processing charges on APCs? So do you have to pay to publish on eLife? I mean, the gold option, it's a way to go open. Let's put it in this way. There is like this economic part of the story. So most of the time, the gold journal, the article processing charges or publication fees, let's say, they are really high, like 4,000 or whatever. And also, let's put it this way. I'm not saying I'm not an expert of eLife, but maybe for example, a cogneuro-oriented community, you have like sort of like target journals you want where you want to submit, for example, neuroimage or whatever, because you want the audience of your paper to be, of course, as generic as possible, but you also want like cogneuro community to read that paper and so on. And if that journal doesn't offer an option, or it offers as an option just a paid one, then going green, it's a free of charge option to disseminate your paper in an open way. And that's why for some journals you have to do it by yourself. And that's also why gold open access option, it's not always the best option, even if it's a totally fine option and it has its own dignity and so on. I don't know if this answered your question.
People who are faculty in the University of Trento are automatically in IRIS. We have to do this to be able to be evaluated by the ministry and to receive potential funds, participating in grants. As a student, potentially you don't have to. So the question was, if you're a PhD student, do you have automatic access to IRIS, and is this visible under the MUER? Or if you have the funds to go open access in eLife, and then you will leave Italy, then being in IRIS is irrelevant, because you will not have to be evaluated by the Italian system.
Okay, so I would say that first, I'm not 100% sure that a PhD student has his own. I'm like 95% sure, because it's part of UniTrento and like doesn't cost anything to just give another, like with Google Drive, Gmail, whatever, Iris, okay. I'd say that for a person who, of course, as most of the time happens, is going to leave to another institution, still, chances are that you publish with someone else in that institution. Yeah, so the record remains there in that institution for the other people who collaborated. And the second part is that IRIS, in any case, it gives you a digital object identifier, so you know that your paper is there forever, and you have always a pointer to the paper. And this is useful to some sense, especially if you published on, for example, a journal which is not open, you want like a permanent link which is accessible by everyone with no subscription. Suppose that you publish in an, let's say, an obscure journal, something which is just for I don't know, mathematician with interest in brain-heart interaction. So chances are that, I don't know, CIMEC has its own subscription, but if you go to whatever other institution, they have not. So it's useful to have a pointer to a paper which is accessible by everyone. And finally, IRIS, it's an archive, but it's many other things. So it's also a sort of hub for the metrics of your paper, which are dynamically updated. So it might be useful to have like a sort of permanent place where the metrics they're going to be always updated and updated, and you can follow the history of the, let's say, the impact of your paper throughout the years. So that's why I would say that also for PhD students and people that maybe would go out from UniTrento with just one publication, it might be useful to fine-tune properly the research desktop, or let's say the publication list, as they say in IRIS. But again, I don't want to sell IRIS. I know that it has many drawbacks, but for several reasons, and also I think the effort is not that incredible. I think the payback it's pretty. It's fair enough, let's say. Okay. Other questions? Okay, I don't know who's the chairman. Okay. I'm finished soon.